In Chapter 13, we've really been working toward a thorough understanding of how to work with multivariable functions and how to perform calculus operations on those multivariable functions. The culmination of Chapter 13, namely Section 13.8 and 13.9, focus on how to best optimize these multivariable functions. So in Section 13.8, we're going to look at how to find both maxima and minima of functions of two variables. So to get started, let's talk about what a relative and absolute extrema looks like in this situation. So we say that a function f of two variables is said to have a relative at a point, which we're going to denote x naught, y naught, if there's a disk centered around that point such that the function takes on the largest value among all of the other values in that disk. We also say that f has an absolute max at that point if it's larger than any points, any function values at any point in the domain of the function. Then we have a similar definition here for relative minimum and absolute minimum. So very similar indeed. The collection of all maxima and relative minima are called relative extrema, and the collection of absolute max and minima are called absolute extrema. So these definitions are very similar to what we talk about in Calc 1 when we talked about optimizing functions. However, in this case, since we're talking about graphs of functions of two variables, instead of lines or curves in two space, these are surfaces in three space. So when we talk about extrema of surfaces, you can think of them in terms of a topographic map as the mountaintops or the valley bottoms of your surface. So exactly what you would picture in 3 dimensions. Now, something that we didn't consider in Calc 1 is this next definition. We say that a set of points in R2 is bounded if the entire set can be contained within some rectangle and it's unbounded otherwise. So the analogy in Calc 1 of single variable functions is an open interval versus a closed interval. Now we're talking about bounded sets and unbounded sets. And we can extend this into 3 dimensions. A set of points in R3 is bounded if the entire set can be contained within some box and is called unbounded otherwise. All right, so this brings us to the extreme value theorem. If f of x, y is continuous on a closed bounded set R, f has both an absolute maximum and an absolute minimum. The takeaways from this theorem are the following. We need our function to be continuous, and we need to be speaking about a closed and bounded set. So those are 3 hypotheses that are required for this theorem to hold. And then if that's the case, it's telling us of the existence of both an absolute and an absolute minimum. So if you can confirm those 3 hypotheses, you can guarantee the existence of an absolute max and absolute min. We have one more theorem here, Theorem 13.8.4, that says if there is a relative extremum at a point, and if the first order partials exist, then it must occur when the first partial with respect to 0 and when the second partial with respect to y equals 0 at that critical point. And so here we say that a point x naught, y naught in the domain is a critical point if both of those conditions hold, or if one or both of the partials do not exist. So this is something that gets left off quite often, is this second clause here. There are 2 ways to be a critical point. Either both of your partials equal 0 at that point, or you have some places where those partials are undefined. So things you need to look for are there any places where we're dividing by 0? Are there places in the domain where, for example, a function is not defined, like the natural log function or an even radical function, things of that nature. So you're always kind of keeping track of the domain of the function, but also where the derivatives are located and where they're defined. I emphasize here the domain in red. That should be your first step in all of these problems. Before you even start computing derivatives, identify the domain so that you know what values of x and y or whatever your variables happen to be that you care about in that particular instance. At the bottom of page 1 here, we want to talk about a saddle point. All right, what is a saddle point? So a surface z equals f of xy has a saddle point, and we're going to call that point x naught, y naught, if there are two distinct vertical planes through this point such that the trace of the surface in one of the planes has a relative maximum at x naught, y naught, and the trace of the other has a relative minimum at x naught, y naught. All right. The reason why they call this point a saddle point is because that's exactly what it looks like. If we think back to our hyperbolic paraboloid, what we referred to as the saddle when we discuss quadric surfaces, it's exactly that point at which the saddle is happening. So let's look at an example here. I'm going to draw an x, y, z coordinate axes. And I'll label them x, y, z. And the equation for the quadric surface that we were referring to as a saddle was, generally speaking, z equals y squared minus x squared. Now, if you zero out the x squared term, you get the parabola z equals y squared. So that looks like an upward facing parabola in the plane of the paper, in the YZ plane. If you zero out the y squared term, you get z equals negative x squared. That's a downward parabola in the xz plane, meaning it's coming out of the paper at you. So I'm going to draw that with a dashed line in the background to indicate that that's actually behind the scenes there. And then what we did to draw this was we looked at various traces in the plane z equals 1 and z equals negative 1 to see the hyperbolas that formed this saddle. And so I'm not going to show that work to find the traces, but what it looked like was we had a hyperbola up top here touching the upward parabola, and then we had a hyperbola turned 90 degrees in front and back coming in this direction. Again, making it dashed in the background. And then we can connect these pieces. And here's our saddle. So let's zero in on the saddle point that is actually located in this quadric surface. So I'm going to highlight it here, and it's right here at the origin. All right, so let's take a look at why this satisfies the definition of a saddle point. So what needs to happen at this point in order for it to be classified as a saddle? It is that there are vertical planes through this point such that the trace of the surface in one of these planes has a relative maximum at that point, and then another plane has a trace where it's a relative minimum at that exact same point. So first of all, we can notice that this is going to be a critical point. And we can do that because if we call this the function f of x, y, notice that the partial with respect to x of this function is a negative 2x, and the partial with respect to y of this function is 2y. If I set both of these equations simultaneously equal to 0, we conclude that both x and y need to equal 0. So what that tells me is 0, 0, 0 is a critical point, which I'll just write as CP. All right, so definitely it's a critical point. Is it a saddle point? Well, we can actually see that it is, because if we look in the plane x equals 0, what we get out is z equals y squared. So let me highlight that in a different color. Here is this trace. And so in that we can visually see, but we could also check using Calc 1, we can visually see that 0, 0, 0 is a min of the green parabola. All right, what's another plane that we could look at, vertical to that point that slices through? We can look at the plane y equals 0. And so that gives me z equals negative x squared. So let's highlight that in a different color. Let's do blue. That's this other parabola. So I'll box that in blue. And we can see there that the origin is now a maximum of that blue parabola. So we can see that this saddle is a critical point and that it's also a saddle based on looking at those two traces of the parabolas and then seeing that, yes, in fact, it is both a maximum and a minimum. So this is a crucial difference from what we learned in Calc 1 to what we're learning here in Calc 3. In particular, when we talked about critical points in Calc 1, there were two options. You were a max or you were a min. Well, technically there were three options. A critical point could be a max, min, or neither. Now in Calc 3, a critical point could be a max, a min, a saddle point, or neither. So now we have this extra condition that we need to check on in order to classify our critical points. So this brings us to what's known as the second partials test. All right, so Theorem 6 says the following. Let f be a function of two variables with continuous second order partial derivatives in some disk centered at a critical point. We're going to define d to be this expression. Personally, I like to express it as d of x naught y naught. You'll notice that they've evaluated these second order partial derivatives at the critical point. All right. And then what we're going to do is we're going to use this d function or d expression in order to classify the critical point x naught, y naught, right? So our goal is to take a look at this critical point and identify, are you a relative max? Are you a relative min? Are you a saddle or what, right? And so we have four different options here. Remember, d is inputting a function with a critical point and it's outputting a scalar value. So the first question is the scalar value positive, negative, or zero? So we have two cases if d outputs a positive value. If d is positive and if the second partial f sub xx at the critical point is positive, then we say we have a relative minimum. If d is positive and the second derivative f sub xx is negative, then we have a relative maximum. If d is negative, no further work required, we can then conclude that it's a saddle point. If d equals 0, we are stuck. We don't know anything. We just say no conclusion. I want to assure you that on upcoming quizzes and exams, I will be providing you this theorem in full, exactly as it's stated. So I'll provide you the d equation and the results. So I don't want you to spend time memorizing this theorem. Rather, I want you to be able to do a couple of things. One is compute critical points, and two is to be able to classify them using the second partials test. So let's look at an example here, starting with number 10. Locate all relative maxima, relative minima, and saddle points, if any. All right, the nice thing about problem 10 is that we're working with a polynomial. And so I'll just make a quick note here that because of that, the domain of this function is all points in two space. And in fact, that merits a smiley face, right? We like it when the domain is all real numbers because we don't have any worries. All right, so that being said, what we would like to do first is identify the critical points because we know that the relative extrema and saddle points occur at critical points. So how do I find critical points? In Calc 1, I take the derivative and set it equal to 0. In Calc 3, if I say take the derivative, you should say take what derivative, right? So we need to explicitly state which derivative we're taking. Let's start by taking the derivative with respect to x. All right, since this is a polynomial, it's easy peasy. We get 2x plus y minus 2. And I set this derivative equal to 0. Now notice this is one equation and two unknowns. I cannot possibly solve this. So what I'm going to do is I'm going to move forward to the partial with respect to y to get two equations and two unknowns. When I take the partial with respect to y, x squared goes to 0, xy goes to x, negative 2y goes to negative 2, and the other terms all vanish. Ah, well, this is nice. This second equation, I can immediately solve for x. X equals 2. I'm going to plug that into this upper equation. So that gives me 4 plus y minus 2 equals 0. In other words, y equals -2. All right, so I would like to write my critical point in 3 dimensions, right? I get the x and the y. The z is just the output of the function f of x, y. So I get one critical point. Let's write it out. My critical point is 2, -2, and then whatever that value is when I plug it into f of 2, -2. That's going to give me my z coordinate. And so when I plug that in here, I'm going to get 4 minus 4 is 0, plus 4 is 4, minus 4 is 0, plus 1 is 1. So my critical point here is 2, -2, 1. Okay, so this is half the battle. We have found the critical point. Next, we would like to identify whether this is a relative max, relative min, or a saddle, or if we can't say anything about it. So what I'd like to do now is I'd like to work on coming up with D. So let's compute those second order partial derivatives. For f sub xx, I am looking up here at the first partial with respect to x, and I'm taking its partial again with respect to x. So only the first term gives me something, and it gives me out the constant 2. Similar for f sub yy, I'm looking back up here at the partial of f with respect to y, and I want to take the derivative again, but with respect to y. Notice that none of the terms in f sub y have a y in them. So when I take the partial again, I'm just going to get out 0. Finally, let me find the mixed second order partial. And to conserve room, I'm just going to write it over here to the side. Let's look up at the one that I have highlighted in yellow. That's f sub x. And now I want to take its derivative with respect to y. So this is the only term that has a y in it. When I take its derivative, I get 1 back out. This just so happens that all of my second order partials are constant and independent of x and y. This is not standard. This just happened in this case. So we'll see in the next example where this didn't happen. So let me set up my D function. D as a function of x and y is the following. The partial of f with respect to x twice is a 2. The partial of f with respect to y twice is a 0. Minus the partial f sub xy squared is 1 squared. And so I just get the constant 1, excuse me, -1. Again, this is independent of xy. So it just so happens that this is d of 2, -2. It doesn't matter what I plug in for x and y. The d function is outputting -1. And this is, of course, negative. So by the second partials test, we are falling into category C, D is negative, and so we conclude that our critical point is a saddle. So I'm just going to note here that F has a saddle at the point 2, -2, 1. I prefer that you write your point in all 3 coordinates, include that Z coordinate, rather than writing it as 2, -2. All right. So again, this function was a little bit easier just because we were working with a polynomial. Domain was all real numbers. Second derivatives led us to constants. And so things greatly simplified. Let's look at a little bit more complex of an example. Let's take a look here at 16. F of xy is xy plus 2 over x plus 4 over y. So first, I would like to identify the domain. This is no longer a polynomial. However, in this particular case, there's only a couple of points here that are going to be problem points, and it's specifically whenever x is 0 or y is 0. So I'm going to write this in the following way. All points in x, y are fine so long as x is non-zero and y is non-zero. right? Geometrically, this means that we are omitting the X and Y axes, right? The X and Y coordinate axes, but everything else is fine. All right. So now let's move forward with finding the critical points. So to do that, I'm going to compute the first derivatives. First, with respect to X. So the first term is going to give me a Y. The second term is going to give me a negative 2 over X squared. And then the third term goes to 0. Remember, we want to set this equal to 0 to solve for the critical points. But again, I have one equation and two unknowns. Not a lot I can do right now. So I'm going to move on to the other first order partial derivative, f sub y. That's going to give me x. The second term is 0. And then the last term is a negative 4 over y squared. And I want to set this equal to 0. So I have two equations, two unknowns. I'm going to solve for one of the variables. I'm going to arbitrarily start with the top equation, but you could work with the bottom equation. I'm going to say that y is 2 over x squared. All right, so I have an equation for y. What I'm going to do now is I'm going to plug that into my second equation. So I have x minus 4 divided by 2 over x squared equals 0. I have now reduced this from a system of two equations, two unknowns, to a single equation with one variable. And so what I have here is x minus 4 over x squared equals 0. And let's solve this. This is x minus 4x squared over 4 equals 0. Certainly I can cancel the 4's out, and I can factor an x out, leaving me with 1 minus x equals 0. So when I solve, I get two values for x, either x equals 0 or x equals 1. But look back up at your domain of your function. Remember, we only care about x, y values where x is non-zero and y is non-zero. So because of that, I'm going to kick this x out, and I'll just make mention this is not in the domain. So this is a good lesson. Always keep in mind what your domain is. You don't want to consider points that aren't in the domain of the function anyways, because they're not even options to serve as a critical point. So we really only have one x coordinate. So then what I want to do is I want to take that x coordinate and I want to plug it in back up here where I have y as a function of x. So then if I plug in x equals 1, I get y to be 2. So I have a critical point here. I have x is 1, y is 2, and what would the z coordinate be? Remember, I'm just plugging that into my original function to get out that third dimension. So that's going to be 1, 2. 2 plus 2 is 4, plus 2 is 6. So here is my three-dimensional coordinate point that is serving as a critical point. So now we would like to classify this critical point. Is it a relative max, relative min, is it a saddle, or can we not say? Because the second partials test is the only thing we have right now in our toolkit in order to identify or classify critical points. So let's go through and compute all of the second order partials, beginning with f sub x. All right, so again, let me highlight up here. First order partial f sub x, I want to take its derivative with respect to x. So that first term, y, goes to 0. For the second term, that's a negative 2x to the negative 2. When I pull that coefficient down in front, I get a positive 4. Subtract 1 gives me an x cubed. Notice that this is not constant. It does depend on x. Let's do the same for f sub yy. Now looking up at this derivative, the x term goes to 0. And similar here, when I take the derivative of negative 4 over y squared, this is going to give me a positive 8 over y cubed. And finally, let's find the mixed second order partial. That one just gives me 1. All right, so my d function is the following. d of xy. Let's remind ourselves what it is. So I'm going to scroll up here. I want to multiply f sub xx times f sub yy, and then I want to subtract off the square of the mixed second partial. So if I multiply f sub xx and f sub yy, I'm going to get a 32 over x cubed y cubed. And then I want to subtract off 1 squared, which is just 1. So here's my d function. I care about what d is outputting specifically when xy is 1, 2. All right, so let's plug those values in. I'm going to get a 32 divided by 8 minus 1. So that is really all I care about, is that it's positive. So now we're down to either case A or case B. It's either a relative max or a relative min. And to figure that out further, we need to look at f sub xx. So I'm going to again evaluate this at the point 1, 2. And if I plug that into f sub xx, I get out 4, which is positive. So let me scroll back up here to the second partials test. We are falling into category A. D is positive at our critical point, and f sub xx is also positive. And so we conclude that that critical point there is a relative minimum. So let's just write that out. F has a relative minimum at the critical point 1, 2, 6. All right. So again, to summarize these types of problems, there's basically 2 steps. First step is find the critical point, and that's by taking the first order partial derivatives and setting them equal to 0 simultaneously to solve for the xy coordinates. And then part 2 is classify that critical point. And that's just a matter of going through the second partials test in order to classify as either a relative max, relative min, a saddle, or if it's if there's no conclusion, just state that. No conclusion from the second partials test. All right, so these examples were all working with finding relative max and min on the entire domain of the function. It may be the case where sometimes we want to find extrema on a particular bounded set, and so that brings us to Theorem 7. If a function f of 2 variables has an absolute extremum, either an absolute max or an absolute min, at an interior point of its domain, then this extremum occurs at a critical point. All right. So this is the first time we're really talking about absolute extrema. So far, we've talked about the second partials test that identifies relative extrema. And so this theorem is just saying, look, if there is an absolute extrema, it's going to occur at a critical point. So critical points are going to be very important to us when finding these absolute extrema. So now, how can we determine absolute extrema on closed and bounded sets? Remember, we just talked about the extreme value theorem that said if your function's continuous and you're looking at a closed and bounded set, we must obtain an absolute max and an absolute min. It must exist. So here's how we're going to go about doing this. You'll see that it's a 3-step process. Step 1 is to find the critical points, okay? And in particular, we're going to the interior of our region. Remember, we're talking about a closed and bounded set. So if we find values that are not in the region, we're going to toss them out. So how are we going to do this? We're going to find the partial derivatives in each coordinate. We're going to set them equal to 0 and solve for x and y. Also, don't forget about identifying where those first order partials are undefined. In our first example, we had a polynomial, so the partials were defined everywhere. In the previous example, our first order partials were just defined at x equals 0 and y equals 0, which wasn't an issue because they weren't in the domain to begin with. But you should always check for that. And then finally, check to see if these critical points are even in the region, because if they're not, then we need to toss them out. Okay, so we have found critical points in the interior. Now we need to check the boundaries. Are there any extrema on the boundaries of your region? So how are we going to do this? All right. First of all, if there are any vertices of the region, include them. So if it's a triangle, include the 3 corner points. If it's a rectangle, include the 4 corner points. If it's a circle, forget about this step because there are no vertices. So identify any vertices. Next, we want to find equations for the lines or curves that form the boundary of your region. Again, if it's a triangle, find those equations of each line. If it's a circle, find the equation of the circle. Whatever that boundary is, go ahead and find those equations. And then what we're going to do is we're going to rely on our knowledge from Calc 1. So right now we've been working with multivariable functions. We'd like to reduce it to a single variable function. So part C, solve for one of the variables in each equation from part B, and then substitute it into the original equation. Remember, f was a function f of x, y, and so if we've solved for one variable and plug it back in, it reduces f to a single variable function. And then we want to find critical points as in Calc 1. So how did we do that? We took the first derivative. There was only one way to take the derivative because it's single variable, set it equal to 0, and then figure out if it's a max or min using the first or second derivative test. Finally, once you have found your critical point in the interior and your critical points on the boundary, you want to just evaluate your function at all of those values. Forget the second partials test. We're not doing any kind of test like that. We're just plugging it into your function. The largest value is the absolute max and the smallest value is the absolute min, and then we're done. So again, I'm just going to reiterate, no second partials test. It's just a matter of evaluating your function at these critical points found in step 1 and 2 and picking out the highest and lowest value. These are traditionally difficult for students, namely because they don't feel comfortable working with the boundary equations. So we're going to work out a couple of different examples so that you can refer to those when you're doing your homework and studying for quizzes and exams. So let's take a look at 32. First of all, we want to find the absolute extrema of f on the indicated closed and bounded set R. 32, we have a nice polynomial function, xy minus 2x, and then R is the triangular region with the vertices 0, 0, 0, 4, and 4, 0. All right, so there's 2 things I always like to do right out of the gates. First, identify the domain, and I'm going to sneak this over here in the margin. I'm just going to note that, oh, look, this is a polynomial, so its domain is all points in 2 space. And the second thing that I'm going to note here is I like to sketch the region that we're talking about, the closed and bounded region, for 2 reasons. Number one, I always want to pick out all the vertices, which they called out here in particular, but they won't always be given explicitly. And number 2, I like to have a visual so that I know whether the points I find in step 1 are actually lying in the interior or not. So what this looks like is the following. We have the XY coordinate axes, and I'm just going to draw the first quadrant. And then we have the triangle. All right, 0, 0, 0, 4, and 4, 0. So this is our region R. And I'm just going to shade it in because that's the region we care about. All right, so just kind of keep that picture in mind as we're working this example out. And now let's move on to step 1. I want to find any possible critical points in the interior of this triangle. So to do that, I'm going to take both first partials, starting with f sub x. That derivative is y minus 2. So this is nice because when I set it equal to 0, I can quickly solve y equals 2. Let's also take the partial with respect to y. So that's going to give me x. And again, this is easy to solve for. I get x equals 0. So I only got a single critical point, namely 0, 2, and then what would the z coordinate be? I just plug those values into f. And since x is in both of those pieces, the whole thing zeroes out. So here's our critical point. Although I will, maybe in this case, write it in 2 dimensions. And then we say, all right, is this in the interior of our region? Well, this point, and let's maybe do it in a different color. If I take a look at this point actually occurs right here. I'm going to cross it out because it's not in the interior of my region. So I did all of this work really for nothing because I found 0 critical points in the interior of my region. I only found a critical point on the boundary. All right, so now let's move on to step 2. Step 2 is to find possible critical points along the boundary. Now, what do we do for this? We need to find, first of all of the equations of the lines or curves that form the boundary of our region. So we have 3 lines that form the boundary. We have the x-axis, which is y equals 0, and so I indicated that there. We have the y-axis, which is x equals 0. And then we have this downward slanting line, which has a y-intercept of 4 and a slope of -1 because we rose -4 and ran 4. -4 over 4 is -1. So this is -x plus 4. So these are our 4 equations here, or excuse me, our 3 equations for the boundary of R. So let me run through each of those different equations. Let's start first of all along the bottom here, y equals 0. So in other words, we're looking at the points between 0, 0 and 4, 0. All right, so what I'm going to do is I'm going to plug y equals 0 into my original function. What that's going to do is it's going to reduce it from a 2-variable function to a single variable function. So f of x comma 0, I'm just going to reduce it to f of x. That gives me -2x. All right. And so now I want to optimize this function just like I did in Calc 1. In Calc 1, I took the derivative and I set it equal to 0, which it can't equal 0. And so I'm just going to note no new critical points. There were no points along this bottom boundary line that could serve as critical points. So to indicate that visually, I'm just going to write little X's along the bottom. I have no possible critical points along that bottom boundary curve. I'm going to repeat this process with the vertical curve, y equals 0. In other words, I'm looking at the points between 0, 0 and 0, 4. All right, so let's evaluate f at x equals 0. So I'll just reduce that to f of y, and this is just 0. So when I take its derivative, f prime of 0 equals 0, and so it's kind of silly, but if I set this equal to 0, yes, it's true, right? All y values are going to satisfy this. So it's silly, but I'm going to write that 0 equals 0, right? So I need to consider all of the points along that boundary. They're all potential critical points. And I had already dubbed one of those in at 0, but what I'm going to do is I'm just going to outline that boundary in red to indicate that those are all possible critical points. So let me write this out in English. Consider all points of the form 0, comma y, where y is ranging from 0 to 4. Okay, I don't care outside of that range because it's not on my triangular region. All right, so we got no points along the bottom, all points along the side. Now let's check along the hypotenuse. The hypotenuse is y equals -x plus 4. All right, so what I'm going to do is I'm going to plug that into my function, f of x comma -x plus 4, which is going to reduce me to a single variable function. And so that is x times -x plus 4 minus 2x, which is negative x squared, plus 4x minus 2x is a positive 2x. So now I want to take its derivative. That's a negative 2x plus 2. And to optimize in Calc 1, I take the first derivative, I set it equal to 0, and I solve for x. And here I get x equals 1. So there is only one possible point along the hypotenuse of this triangle where I might possibly get where I have a critical point. How do I find the y coordinate? I'm just going to plug it back up into this equation for the hypotenuse. So y equals negative 1 plus 4, which is 3. So I have the point negative 1, 3. So let me indicate that in red on my triangle, roughly right here. All right. So the points that I have kind of highlighted in red are the possible critical points. Remember, I didn't find any in the interior of the triangle, which is why you don't see any red dots in the triangle. And so now the final step, step 3, and I'm going to scoot out here because I'm running out of room. I just need to evaluate my original function at these points, the original function. No second partials test. I don't need to compute any second order partial derivatives. I'm just going to plug these points in. All right, so let's start from the top. I had no points in step 1. In step 2, part A, I had no points. So let me just highlight in green the points that I need to test. I need to test points of the form 0y for y ranging between 0 and 4, and this single point on the hypotenuse, negative 1, 3. All right, so let's do it. Let's first evaluate f at the point 0y. That gives me 0 minus 0, which is 0. All right, next let's evaluate it at this other point, f of negative 1, 3. That is going to give me negative 3 plus 2. Which is negative 1. Okay. And then the only other point I want to do here, whoops, darn it all. I just noticed that this shouldn't be a negative 1. So let me fix that. This should be plus, which makes this plus. And so let's correct this. This becomes 3 minus 2 gives me 1. That looks a little bit better. All right. And then remember, there was one other set of points that we need to consider. We need to consider all of the vertices. So maybe up here in blue, I'm going to list my vertices. Oh, actually, no, they're already listed. So I'll just highlight them here for you. We need to consider all 3 of these vertices. Now, because I plugged in the point 0y, I've already taken care of these 2 vertices. So I just need to check this one vertex to see if it's a extrema. So I'm going to plug in f of 4, 0, and what does that get me? That gets me 0 minus 8, which is negative 8. All right, so now take a look at the 3 values you got out. Let me circle those values in purple. We got out 0, we got out 1, and we got out negative 8. The largest value serves as your absolute max. The smallest value serves as your absolute min. So let's just conclude this. I'll write it in the margin here in purple. We have an absolute maximum value of 1, and that occurred at the point 1, 3. And we have an absolute min of negative 8, and that occurred at the vertex 4, 0. All right, so don't forget about those vertices. They're so important because they are places at which that function could take on a max. Geometrically, how can you interpret this? Remember, this function f of x, y, it's a surface in 3 dimensions. So it could be bouncing above the XY plane or below the XY plane, depending on what Z values it takes on. So what you should think about is if you are in space in an airplane and you have a bird's eye view and you're looking down at this surface that F describes, the mountaintop over this triangular region that I've graphed here in the XY plane, the highest point over that triangular region has a Z coordinate of 1, which is what we just wrote, and it occurs on that hypotenuse point 1, 3. And then the lowest valley is right there at that upper vertex, the side vertex, 4, 0, and that has that minimum value of -8. So again, it's just kind of looking as a bird's eye view what the highest and lowest Z value is. All right, 36 is another example of finding an absolute extrema on a closed and bounded set. And thankfully, we're still working with a polynomial, so that makes our domain easy. I'll just make a note of that here. The domain of our function is all coordinate points in 2 space. And then let's take a look at what our region is. It says the region satisfies the inequalities x greater than or equal to 0 and y greater than or equal to 0. What that means is that's just points in the first quadrant. So I'll sketch that here. The equality with 0 allows us to lie on the x and y axis. And then the third inequality says x squared plus y squared is less than or equal to 1. That's all points on or inside the unit circle. So I'll sketch that quarter circle right here, indicating that it's radius 1, and it's also everything inside there. All right, so we may want to just start by listing the vertices so we remember to test those. There are 3 vertices here. There's 0, 1 up top. There's 1, 0 on the side, and then there's the origin 0, 0. So let's go ahead and just make those red so that we don't forget. I should have maybe done that in the last example, made the vertices red. Those are for sure points that we're going to test. All right, so now let's begin with step 1. Let's find any critical points that might occur in the interior of our region. So the partial with respect to x is y squared. And if I set that equal to 0, I get y equals 0. And the partial of f with respect to y is going to be 2xy. All right. Y is already 0, so x can be anything. So what this is giving me is points of the form x comma 0. So are these in the interior of a region? No, they're not. So I'm just going to cross out. This is not in the interior. So we struck out here in step 1. So let's move along to checking our boundary lines or boundary curves. All right, so next we need to come up with equations for the boundary lines and curves. The straight lines are easy. The x-axis is y equals 0 and the y-axis is x equals 0. So then how about this circle? We know that it's x squared plus y squared equals 1, but let's solve for one variable. We have y squared equals 1 minus x squared. Normally, if I'm square rooting both sides, I'm going to be very careful to include a plus minus. In this particular case, I only care about the positive y values, right? Because I'm in the first quadrant. So I only care about y equals the positive square root of 1 minus x squared. And I write that plus sign there to emphasize that I didn't forget about the plus minus, but I only care about the positive square root because I want the upper semicircle. And more importantly, just the first quarter circle. All right, so let's check our easy ones first. Let's look along the bottom line, which is y equals 0. And I'm going to plug this into my function. That gives me f of x0, which is f of x, and that just gives me 0. So we saw this example up above in part 2b, where the function equals 0, which tells me that the derivative equals 0 and 0 equals 0. So all points along this boundary line are critical points that should be considered. So we're going to consider all points x0, where x is only ranging from 0 to 1. All right, so let me highlight those points there. Those are all the points along the bottom of this quarter circle. All right, we need to test them all. So now let's look at the next one, x equals 0. Same exact thing. We have f of 0 comma y, which is f of y equals 0. So here I want to consider all points 0 comma y, where y is also ranging between 0 and 1. If it's outside of 0 and 1, it's not on our region at all. So I'm going to now highlight this entire other straight side. All right, so the one that's going to be of interest is going to be the curved boundary line. So let's see what's happening along y equals the square root of 1 minus x squared. All right, so I want to plug this into my function. So this is the function f of x comma square root of 1 minus x squared. I'll just now refer to this as f of x. I want to square that y coordinate. So this is x times 1 minus x squared. I'm going to go ahead and distribute that so that I can take the derivative easily. And so now I'm in the world of Calc 1. This is a single variable function. I want to find its critical points. So I take the first derivative, I set it equal to 0. That's 1 minus 3x squared equals 0. And so here I'm getting 2 points, x equals plus or minus the square root of 1/3. Now, keep in mind our x values, right? This region, this quarter circle, is only considering points where x is between 0 and 1. So toss that -1 right in the trash. All right, that doesn't fit in our range. But the square root of 1/3 definitely is between 0 and 1. So we do need to check that one. All right, so that being said, we're looking at the square root of 1/3. What's the corresponding y value? Remember, you just want to plug that back up into the y equation. And so if x equals the square root of 1/3, then y is the square root of 1 minus, when I square x, it's 1/3. So I get the square root of 2/3. All right, this is a new point that we need to consider when we're checking our critical points. If you want to plot roughly where that is, we want to go over square root of 3 and up square root of 2/3. I don't really know, but I'm going to just eyeball it and say it's right there. I don't feel real good about the accuracy of that point though. All right, so now we have all of the points. Let's highlight the points that we need to check. All right, we need to check the vertices. We need to check points of the form x0. We need to check points of the form 0y. P.S. that covers all of our vertices. And then we need to check, I didn't write out this last point, so I'll do that right now. Square root of 1/3, square root of 2/3. And so let me highlight that point. So here's a list of all of the points that we need to check. Let's go ahead and test them. So here's our test. F of 0y is 0. F of x0 is 0. F of root 1/3, root 2/3. What's that one? That's going to be root 1/3 times 2/3. And so you can just write this as 2 over 3 root 3. If you want to rationalize that, you most certainly can. That's up to you. And so here we have it. Here are the z values, 0, 0, and 2 over 3 root 3. The highest value is your absolute max. The lowest value is your absolute min. So not much of a contest here. We have an absolute max of 2 over 3 root 3, and this is occurring at root 1/3, root 2/3. And we have an absolute min of 0. And this is occurring kind of at weird points, right? So I'm just going to list them as x comma 0 and 0 comma y. And this is for x and y values ranging from 0 to 1. Remember, just those two pieces there along the side and bottom of the quarter circle. So this is my final conclusion for the absolute extrema of the given function xy squared when taking a bird's eye view down at that surface over that quarter circle in the xy plane. So again, I cannot stress enough to really practice these problems. There are so many steps and there are so many places to make mistakes, and even I made a mistake up top with a sign error. So just be very careful and very diligent when you're working these problems out. We're going to conclude these notes with one more example, but thankfully it's not on a closed and bounded region like the last two examples, so it's not quite as bad. What this is a word problem, and we want to optimize this. All right, so let's just look at what we have. Find 3 positive numbers whose sum is 27 and such that the sum of their squares is as small as possible. So let's translate this English statement into math first of all. We're working with 3 positive numbers, so give your numbers names. They can be XYZ, they can be ABC, they can be X1, X2, X3, whatever you're comfortable with. I'm going to use XYZ. So let X, Y, Z be positive numbers. All right. Now, we want their sum to be 27. So let's set up that. We have X plus Y plus Z equals 27. And then what we want to optimize is the sum of their squares. We want that to be as small as possible. So let me set up that function. F of X, Y, Z equals X squared plus Y squared plus Z squared. And our goal here is to minimize this function. All right, so when we think back to the name of this section, we're trying to find maxima and minima of functions of 2 variables. Wah, wah. We have 3 variables right now. What the heck? The good news is we have this extra equation that we can use to reduce one of those variables. So let's just cut Z out of the equation. If I solve for Z, Z is 27 minus X minus Y. So what I'm going to do is I'm going to just plug that into my function, F of X, Y, and then 27 minus X minus Y. And I'm going to give this a new name. I'm going to call it just F of X, Y. So what this is X squared plus Y squared plus the quantity 27 minus X minus Y squared. All right, so now we're back to a situation where I have a function of 2 variables, and in this case I want to minimize, right? I want to find the relative minimum. And so now I'm going to go through my process of finding the critical points and then using the second partials test to identify if the critical point that I found is in fact a minimum. All right, so we're looking for our critical points. To do that, I want to take the first order partial derivatives and set them simultaneously equal to 0. So what is the first derivative with respect to x? So I'm getting 2x plus 0, and then I'm going to use the chain rule here, plus 2 times 27 minus x minus y, and then that'd be to the first power. Derivative of the inside with respect to x is a -1. All right, so let's go ahead and simplify this. This is a 2x plus 54 minus 2x minus 2y. And shoot, I didn't distribute my negative times a negative 1. And so this becomes 4x minus 54 plus 2y. All right. So what I have here is one equation, two unknowns, right? So set that equal to 0. Let's do the same for f of y, or f sub y rather. So I get 0 plus 2y plus 2 times 27 minus x minus y times negative 1. And so I'm going to similarly get 4y plus 2x minus 54 equals 0. So I need to solve these. As we've been doing previously, it's best if you can solve for one variable and plug it into the other equation. What I might do instead, scrap that. Let's take a look here at the first equation. If I solve for y, I get y equals 54 over 2 is 27. And then subtract the 4x over, negative 4x divided by 2 is negative 2x. And then I can just plug this into the second equation. So what I have is 4 times 27 minus 2x plus 2x minus 54 equals 0. So one equation, one unknown. That is a negative 8x plus 2x gives me a negative 6x. 27 times 4 is going to be 108. Minus 54 is a leftover 54. And this equals 0. So in the end here, I'm going to conclude that x is equal to 54 over 6, which is 9. All right. This is a positive number, so it checks out in that regard. And then you can plug this back up in your formula to find y. Y is 27 minus 18, which is going to be 9. All right. So what we got here is the potential critical point, 9, 9, and then what would the z coordinate be? Okay, so then you just want to go back and plug it in up here. So that would be 81 plus 81 plus 27 minus 9 minus 9 squared. And so, nope, that's not what I'm looking for. Let's actually plug it into this z equation. So I misspoke here. So let me erase what I just have written here. All right, z is 27 minus 9 minus 9. I was actually finding the w coordinate in the fourth dimension. I just want z. So this is going to be another 9. All right, so here's our critical point. And the question remains, is this a max, min, or saddle? Our goal was to minimize the sum of the squares, so we sure hope that it's a minimum, but we don't know yet, so we should prove it. So now let's begin by setting up our D equation. We need to find all of the second order derivatives. So when I take the derivative of f sub x, which I'll box in or I'll highlight up top, when I take this derivative with respect to x, I get out 4. When I find f sub yy, I'm looking at this derivative. When I take its derivative with respect to y, I also get out 4. When I find the mixed second order partial, okay, look up here at this first derivative and take its partial with respect to y, I get out 2. So our D equation is 4 times 4 minus 2 squared. 16 minus 4 is 12. This happens to also equal d of 9, 9 since it's constant, and that is positive. So remember, there were two cases in the second partials test. If you were positive, you then needed to go and look back at f sub xx, but notice here it's constant and it's always positive. So f sub xx at 9, 9 is also positive. And so by the second partials test, we conclude that we have a minimum. All right, so let's look back up at the statement of the problem. What are we looking for? Find three positive numbers whose sum is 27 and such that the sum of their squares is as small as possible. So what we have is x equals y equals z equals 9. Those are the three numbers. And the sum of their squares is 9 squared plus 9 squared plus 9 squared. 81 plus 81 plus 81 is 243. So here's our final answer. Whew! All right, so that was our notes for finding maxima and minima of functions of two variables. And we're going to finish out chapter 13 with section 13.9 talking about Lagrange multipliers. It's going to play exactly off of what we talked about in 13.8. However, we're going to be optimizing functions subject to a constraint. So that is coming up next.